Okay, hello everyone. We are here to do a little exploration of version 13.2, which just came out, is now live and ready to download, available in the cloud. Um, and I'm going to show you a few things that are new in version 13.2. So 13.2 is, by our standards, a fairly modest release. It's kind of a polishing, finishing type release for a bunch of features and a starting release for other features. Kind of our strategy is to try to do 2 releases per year at this point, to give you all kind of the benefit of the latest that we have achieved in our R&D pipeline. And we'll talk about today things that have been in that pipeline for 5, even 10 years, and things that are also just arrived in the pipeline within the last year and are now done. So there's a kind of a collection of different things coming off this R&D pipeline over time. It's kind of a picture. This is a piece that I'm going to be going through what I talked about here in this piece, and you can find the piece also on the web. I kind of launched that piece with a picture here showing kind of the version history of Mathematica and Wolfram language, starting from 1988 and taking us all the way to 2022 and version 13.2. And you'll see there's sort of a higher density of releases developing here in more recent years. You will also see, if you were to look at a different plot of the amount of functionality as a function of time, you'll see sort of a rapid increase over the last decade or so, but a steady increase through all of this time. But anyway, so 13.2 follows its many previous releases, and it has a bunch of interesting things in it. So what's new in version 13.2? Well, as I say, by our standards, a fairly modest release. The number of new functions, completely new functions in version 13.2 is only 41, I believe, which by our standards is modest even for a 0.1 release, but it's still a large number. Now, in addition to that, there are 64 functions which are substantially enhanced in version 13.2, and there are just a huge number of things that have been fixed, thousands of bugs and such like fixed, and so on, and lots of additional polish that's been added. By the way, the functionality that I'll be showing, a lot of that functionality was worked out in design meetings, which were live streamed. There have been about 60 hours of live stream meetings related to functionality that's in version 13.2 over the past 6 months or so. I should explain that version 13.1 came out just in late June of this year. So we're a little bit less than 6 months from our previous release. We have this release. All right, what's new here? Well, one area that's pretty big, and we're just seeing the beginnings of it in version 13.2, is astronomical computation, astro computation functionality. So let me walk through a little bit about how astro computation works in Wolfram language. Over the past decade or so, we've added pretty sophisticated geocomputation capabilities where we're able to, where we both have a lot of data about geographic things, and we're also able to do, I think, probably the world's finest kind of geodesy computations about where things are on the Earth and distances between them and all those kinds of things. Well, now we want to flip things around, look at the sky, and do those same kinds of computations for the sky. The main issue with the Earth is parameterized by latitude and longitude. That's the sort of canonical way to determine a point on the Earth. There are differences in the ways that you render. The most obvious difference when you're looking at making maps of the Earth, the most obvious difference between different maps is how the Earth is rendered, how the sphere of the Earth is rendered in 2 dimensions, the projections that are used, and so on. But in the case of astronomy, things are even more complicated because there isn't a very obvious latitude, longitude set of coordinates. Well, maybe there is from this moment where you are standing on the ground at a particular place at a certain time. You look up in the sky and you can see the altitude, the angle up from the horizon, and the azimuth, the angle from north of a particular point on the sky. But you wait 5 minutes and the thing that you thought you were looking at has moved in quotes because the Earth has moved, and so that isn't giving the altitude and azimuth isn't enough. Isn't a convenient way to specify things because then this so-called fixed star has moved to different position in that regard. All right. So how does astronomy stuff basically work? Well, here's oh no. Okay. All right. Hopefully that dialog won't come up every time I do this. The this is a typical thing that we would get in the new astronomy functionality. That's the position of the planet Mars. Now let's do the corresponding thing. Let's say I say geoposition of let's say New York City here, and that would give us on the Earth, that's the geoposition of New York City. Now, conveniently, New York City doesn't move over time. And so this geoposition is just a fixed thing that we can compute once and for all. The planet Mars does move over time. I bet if I recompute this again, oh, look at that, it moved. And the main reason it moved is because what we're showing here is azimuth and altitude. Those are things that tell us where Mars is in the sky from where I am right now. So it tells us it's at 8 degrees above the horizon, which is very close to the horizon. If I open this up, I can see it's actually not my actual location, it's my virtual location here. So it isn't in fact at that angle in the sky where I am. It's at a different angle where I am because it doesn't know my actual current location. So let's see. So this is kind of a way of that's that astro position, and we know about many kinds of objects. So we can say, astro position of the star Sirius, for example, and that will now give us the position of that star in the sky where it thinks we are. Okay. Okay. So the question is, what are appropriate coordinate systems to use? If this is going to come up every single time, it's going to drive me absolutely crazy. Let me see how to do this. Let's see here. All right, so this is now showing us the position of Mars in a more robust let's see, maybe somebody can tell me how to fix this dialog. I think I should be able to go to preferences. Yeah, this is unfortunately going to really blow us up if this doesn't work. Well, I'm trying to avoid retyping everything here. Okay, in any case, back to this. So let's see. So the issue here is, what's a better coordinate system to use than one that is sort of fixed to where you are on the Earth? And the most immediately kind of astronomer-friendly solution is to use so-called equatorial coordinates, which work with right ascension and declination. And so it's basically looking at angles, imagining that you are based at the center of the Earth and you're looking outwards, and these are angles defined for where is Mars relative to the center of the Earth, looking outwards from the center of the Earth. But now these angles are defined by two different directions. One is the one direction is the rotation axis of the Earth, and you need one other direction, and the direction that's picked is where the sun is at the time of the spring equinox, which is, I think, the same as the first point of Aries, if I remember correctly, in the constellations. That may not be quite right, because I think there's a precession of the equinoxes, so it's all complicated. Okay, in any case, so this is just a different coordinate system for looking at for representing where astronomical objects are. And if we compute this again, we'll find it's moved a little bit. But if we were to compute, for example, the astro position here again, let's do that again, it will have moved a lot. It will have moved by a whole degree here, because this is moving because of the rotation of the Earth. This is only moving a lot less because of the fact that Mars is moving in its orbit. And so every time we actually ask for that position, those things will be recomputed. So, okay. Let's see. I can't do that. Let me see. Let's just try something here. We were having trouble. Yeah. Okay. How do I get rid of this? Anybody know? Is there a preferences setting I can go to?
What do you mean? How do you get rid of it?
Is there a way to tell it not to produce that thing and just say
no?
Okay. Well, then we set this up wrong. Okay. All right. Okay. All right. Thanks. Okay. Well, let's see. Going back to this. So I think what's going to happen here, yeah, this is going to be a bit of a mess. Sorry, guys. Yeah. Let's see here. Okay. All right. Well, all right. We'll try to work around this. Okay. So as I was saying, we're talking about astronomy functionality, and this whole idea of where things are astronomically, so to speak. It's the first thing one has to solve in doing astrocomputation. So this equatorial coordinate system is good if you think of things in terms of us typical Earth dwellers, so to speak. However, if you're, for example, on a spacecraft, how can you refer to the position of Mars if you're somewhere, traveling to Mars, or if you're somewhere near Venus or something like that? You don't really want to refer to the position of Mars relative to the center of the Earth. You want some more global coordinate system. And a standard way to do it is to use the so-called ICRS frame, which is where the thing is sort of centered not at the center of the Earth, but at the center of gravity, center of mass of the solar system, which is roughly the center of the sun, but not quite, because Jupiter is big and things like this. So now this is now a different coordinate system for representing the position of Mars, and one that doesn't depend on the where the Earth is in its orbit. It has nothing to do with the Earth. It's a more sort of global coordinate system. But nevertheless, one of the things we're doing here is we're showing the result in terms of angles, and there are standard directions that these angles point in. We can also get it in Cartesian coordinates, where we have an actual x coordinate, y coordinate, z coordinate in that particular frame, where we've got kind of a triple of coordinates centered at the center of mass of the solar system, and we're saying where Mars is in that coordinate system. Okay, so in the typical way that this kind of thing works, we can say, get me the data from this astroposition object, and there we've got those three values, and then we can go and plot things there and so on. I'm sure if I were to do, I'm just now curious to do this because I got to have some fun here. Let's see what happens if I were to say this, and I were to just say planets here. Actually, I might want a list of planets. Let's get an entity list of planets, and let's see what I can compute. So it's got to work out, oh, it's got to download. Ah, yes, this is interesting. So it's got to download the all of the data that it needs to know the positions of all these planets. And so what will happen is it will download the data that it needs for each planet, and then okay, it gets all of these. Actually, what I should have done here is I should have said of data here, and then there we go. And now I can say list point plot 3D of that, and I should have the positions of all those planets. That's interesting that they're, I would have expected them to be really in a plane. I wonder why they're not. Okay, maybe Jose is here. Maybe he knows the answer to that question. Why everything isn't coplanar. Maybe it is coplanar, but this axis is different here. Let's see. If I say what would I need to say? I would need to say box ratios, arrow automatic. And that might, still interesting. Okay, so the planets are not that coplanar. Maybe that's I have a great urge here to just say I see, maybe they are in a plane, and we just have to line up the plane appropriately. Or maybe they do look like they're kind of in a plane here. Maybe we should do this for some anyway, okay, but in any case, this is getting us the current positions of all of those planets. All right, and we can do the same kind of thing for lots of other kinds of bodies in the solar system. Let's get the position of Ganymede or something like this. A fun thing to do is to say, where was Ganymede at a particular position, a particular time? So this is asking, Galileo turns his telescope to the sky. He said in the first hour of the night on January 7th, 1610, and he was in Pisa. I think maybe he was in Padua actually at that time. But anyway, the I think we have this wrong actually here. In any case, we can then compute based on the data that we have. We can compute where was Ganymede in the sky, and actually it's interesting that it was altitude 43, so that's why he was able to see Jupiter at that time, because it was fairly high in the sky from where he was. So, okay. We can also ask a question like, where is Venus from the center of Mars? So this is now telling us, we don't call it altitude and azimuth anymore, because it's that's not yet the, maybe the Mars colonists will have a name for it, but right now we have different names here, but that's the that's the corresponding result if you were starting from the center of Mars. I think that's actually probably the equatorial coordinate system of, yes, because we didn't tell it. We just told it the planet Mars. We just gave it a position there, and we're not telling it. I bet if we say, let me live dangerously and see if this works. The only feature on Mars that I know is probably Olympus Mons. Let's just see if we oh, look at that. Altitude and azimuth. Okay. So if we were hanging out at the tourist spot at the top of Olympus Mons or whatever, that's where we would see Venus in the Martian sky right now. Okay. All right. We can look at things like, what was the position of the sun at the time of sunset today? And you can see, yes, its altitude is the time when I guess the sun is slightly below the horizon at sunset. And why is that? Well, part of the reason for that is that there are all kinds of corrections that you have to make in terms of, okay, this is where things start to get very complicated, because you're dealing with things like the refraction of light through the Earth's atmosphere. So the position of the sun as seen from you on the Earth is the position of is the direction from which the light ray that reaches your eye is coming, and that's affected by the bending of light as it goes through the atmosphere of the Earth. So that's one thing, and then there's the whole can of worms of the speed of light. And so, for example, let's say we look at the planet Neptune, and we ask the question, what's the astral position of the planet Neptune at a certain time? Well, it's going to depend whether by at a certain time we mean for the light to arrive on Earth at that time. Where was Neptune in when the light arrived on Earth at that time? Or where was Neptune if we back calculate where would it have been at the time where we've kind of said that it should correspond to the time of yeah, I mean, this is I'm explaining poorly. Let's see. I mean, it's kind of like where Neptune quotes actually is, or where we observe Neptune to be. But the statement where it quotes actually is, the whole lesson of relativity, is that that's not a completely sensible question to ask, because it depends on the reference frame, it depends on how you set up the simultaneity surface and so on. But we have a variety of choices for that that do or do not include light travel time in the computation. So, okay, so that's some of the complexity of saying where things are astronomically. Well, what can you compute from knowing where things are astronomically? One thing you can compute is how far apart are two things. So, for example, the astronomical distance between Venus and Mars, we can just go ahead and compute. We can compute the distance from us to some particular thing. So this is, for example, let's find out what this is. This is the position of the Viking 2 lander, and that's represented by a geoposition on Mars. And we ask what's the astro distance to that geoposition on Mars, and it will give us the result. Similarly, if we want to compute the distance to a star, we can go ahead and do that. And that's in astronomical units. We could convert it, if we say unit convert to light years. That's a bad autocomplete. That should be set up to start with light years, guys. It's about 12 light years away. So let's see. Again, when you compute an astro distance, you need to know both what the thing that you're computing, you need to know both where you're observing it from and when you're observing it. So this is the distance to Mars here and now, so to speak. And I'm sure if we compute it again, we might get a slightly different answer. There we go, because Mars is moving and the Earth is moving. And for example, here's a list. We can just, for fun, we can compute this with 1 second pauses. We can compute the distance to the Apollo 11 landing site. Let's compute it 5 of those positions, and we'll probably find, there we go, let's take a look. We'll probably find, actually, I'm now curious how big these are. Okay, let's unit convert this to, let's try it to meters. Okay, so that's the distance over the 1 second delay. That's the change of the distance to that Apollo 11 landing site as the Earth and the Moon move. Okay, so we can now compute things over longer periods. We can observe different kinds of phenomena. For example, let's say we're computing the distance to Mars every day in the next 10 years. This would be how we would compute that. And you see it wiggling around, and it's being perturbed, no doubt, mostly by Jupiter in its orbit. And so it's not just a straight, 2 ellipses, and how far apart are they? Now, we can also compute things like the angular separation from the Earth of different objects in the sky. And again, this is angular separation from here at time t between Jupiter and Saturn in the sky from 10 years ago to 10 years in the future. And there we see the result. Okay, so that's kind of raw astro computation, and we'll be steadily adding in capabilities for dealing with orbits of satellites around the Earth, deep space probes, all this kind of thing, the celestial mechanics, kind of real-time celestial mechanics of all these kinds of things. Right now, we've primarily worked on solar system objects and fixed stars. We haven't yet worked on the cosmological version of this, going out to the edge of the universe, but all of that is coming, and we now have sort of the infrastructure to be able to set up computations in the universe astronomically. Okay, well, another big piece of this is astrographics, the analog of geographics. This is not as well developed yet in this version. We just have sort of experimental version of this now available here. And so what you'll see here, there's the star Betelgeuse and some stars that are in our data set of stars that you see nearby, and this is in the constellation Orion. If we zoom out, just like there's a geo range for geographics, there's an astro range for astrographics, and there we're zooming out a bit, we can see Betelgeuse sort of contextualized in these different with respect to different stars. Now, things are complicated when you make these pictures. You have to say a lot about where you are as the observer. There's the astro range. The astro reference frame is kind of what coordinate system do you want to use to make this plot. That's kind of the beginnings of that's kind of which way is up and so on. Then there's a question of, well, what do you actually want to use as the background here? Just for example, for geographics, you can say, I want a background that shows a satellite image of the Earth, or you want a background that shows a map and so on. So let's do this. This should give us kind of, you can see the little bit of the Milky Way here. That's coming from the astral background of the galactic sky. Different reference frames, so we've reoriented Orion because it's different way up because we're in a different reference frame. So we've changed which way is up. And just for fun, we can do something. We've got nice little illustrations. You can go back to Babylonia, so to speak, and get the full story of what were these constellations supposed to be. That's complete with whimsical bulls and unicorns and other such things. Now, what you're drawing here is always a projection of the sky, which is kind of a thing with angles. Kind of, you can think of the sky, as various ancient cultures have, as kind of a giant dome, and the stars are painted on the inside of that dome. But we get to, when we render it, we have to say, what projection are we going to use to turn that into something which is flat, that we can just put in a notebook? And so we have the notion of an astral projection, just like we have a geo projection. In fact, the same projections that we can use for geo, we can also use for astro. So this is Lambert azimuthal projection, and you see there the Milky Way forming a that red line is for the galactic, the plane of the galaxy, just as the blue line here is the equatorial plane, and the yellow line here is the plane of the ecliptic, the plane of the solar system. You see all the planets lined up along the plane of the solar system. And we can probably go through here, and let's pick another. Let's try mole-wide projection. We'll pick a different projection of the sky. There it is. And so now the plane of the ecliptic is no longer straight, and we're just seeing a different projection. There's a projection quite often used to show like the cosmic microwave background and other such things. Okay, or we could pick, if we want to see if we want to ask the question, if we were to look from the Earth and we were to say, what can we see looking out up into the sky? That is essentially a stereographic projection, and that's a way that we could make that stereographic projection, which is kind of the analog of what we're doing here. I see a question coming in about, can one do astrology with Wolfram language? For sure, you can compute. I think the science part of astrology is all about computing, when is this planet in the ascendant and things like that. Absolutely, you can compute that stuff very well. The connection between that and earthly affairs is a different story, that we're out of that business. But in terms of knowing what's happening in the heavens, we're in good shape on that. Okay, so we can zoom in, for example, here on, let's take astral range of 10 minutes of arc on Jupiter. Oh, look at that configuration. We've got the moons of Jupiter lined up, Io, Europa, Ganymede, Callisto, all lined up on one side of Jupiter at the present time. Well, of course, we have to say, let's look at the classic, and let's look back at old Galileo, and let's see, and on the that construction I'm not used to from classical Latin, but anyway, the 7th day of January, Instantis Anni 1610, hora sequentis noctis prima. Okay, the first hour of the night. This is what he saw, and that's, I guess that's the that must be east, and that's west, orient and occident or something. And this is now showing there's Jupiter, and through his telescope he saw those new stars. Just for fun, we can of course use Wolfram language to do the the text recognition from that piece of text here. And one of the languages for text recognition is Latin, so we can go ahead and do that. And we didn't get the word space there. Shocking. Anyway, so this gives us the information, and now we can go ahead and compute for his position, which, and I think I said it wrong in the previous place in the blog, his position in Padua. We can go ahead and compute what was the configuration of these moons at the time he saw it, and that's the answer. So that's one, another, and we see what it is. And by the way, notice it's a different configuration from the one that we see today. And what he saw over successive days was the motion of those moons. Okay, actually, we can. I just have to try this. I'm just curious what he would have seen 1 week later. Let's see, +1 week. Ag. Right. Just +1 week here. Well, that's interesting. Callisto has disappeared. Okay, now I have to do it for 2 weeks. And I guess that okay. Okay. They've moved quite a bit there. And that's a random star that showed up in the frame in this particular case. Okay. Well, just to check out a few more things astronomically, and then we're going to move on to different topics. Yeah, the reason that a star appears here is because, needless to say, in 2 weeks Jupiter moved, and so it's now on a different star background. And I'm sure if we said, let's see, astro background of galactic sky, we would probably see a bunch of other, we'd see a bunch of other kind of fuzzy stars here, representing kind of where this is in the sky. Okay. And we're zooming in a long way, so our background is, we're going to have progressively better backgrounds, but this is still showing the background is rather fuzzy. It's like we were on a satellite image and we zoomed in so that we were looking at things a centimeter across on the Earth or something. Okay, let's look at an eclipse, for example. Let's ask for the solar eclipse of October 2023, and let's ask that's the time of maximum eclipse, and so let's look at that from a place that is in the path of the eclipse, and there we go. We can see that the moon is just about to cover the sun there, and that's what we would expect in an eclipse. And eventually, we will have a bunch of abilities to compute syzygies like eclipses, coincidences of things like this, and that's one of the great things that we get from our kind of astro computation capabilities. Okay, well, that was a little bit on astro computation. I think I went on longer than I expected about this particular topic, but that's the story for that. And this is a kind of a big new thing that's just rolling in to in version 13.2 of Wolfram language. All right, let's go to something different now. Let's talk about dates and times. And we've done a huge amount of work on dates and times. We needed that work, actually, so that we could get to things like astronomy, because unless you know exactly what time it is and you have a good way to represent that, you can't really represent astronomical kinds of things. So we've got everything we could possibly have for dates and times, but we still had a few more things that we've added. So, for example, one thing we have now is random date. You could pick a random date in the year. We could pick a random date in a particular time period. Oh no, not that again. Okay, plan B. Okay, so one thing that's tricky is if you say I want a random date, one of the things about dates is that you have to give a granularity for a date. Just like a number, you are giving 1 second here. It's very odd. Weird. Just like you say what precision of number. If you pick a random real, you can say what precision of real do you want to get. Here you can say what granularity of date do you want to get. This is day granularity. Okay, so for example, 10 random times during the next 6 hours. Let's go ahead and get that. We can do this. You can compute. It gets a little tricky with dates to be able to compute sort of uniform dates, uniformly distributed dates over periods of time that might be described in a way that seems uniform, but actually that time period is different. And so you have to correctly deal with that in selecting random dates. Okay, next topic about units and things is the story of, so dates and times are incredibly complicated. There are calendars, there are leap years, there are leap months, there are leap seconds, there's all kinds of stuff going on. There's different cultures with different calendars and so on. All of that stuff we've now taken care of. Okay, let's turn to a different area, which is units. We have 10,000 kinds of units in Wolfram language. They have units are kind of a way of describing things about the world. Here's a tricky issue. Tricky issue is temperature units, because there are, when you say it's 20 degrees centigrade, you are the zero of that 20 degrees centigrade is the melting point of water, the freezing point of water, melting point of ice, but it's not a sort of true zero. If you say the length of that thing is 0 meters, you mean something which is sort of, you can multiply by that 0 meters and get meaningful things. With temperature, the zero of temperature isn't sort of an ordinary multipliable by number. It's just this arbitrary place. Now, the only place that isn't true is with the Kelvin scale, where one's dealing with absolute temperature, where absolute zero really is the temperature at which, sort of most motion ceases. The average kinetic energy is just the little quantum 0 point energy for things. It's a true zero of temperature. But when you're dealing with degrees Fahrenheit, for example, you're not dealing with the scale of temperature where 0 degrees Fahrenheit really is absolute zero. So that leads to all kinds of trouble. So the number 8 here represents something that you can't, if you just say degrees Fahrenheit here, you can't multiply by that number 8 and get anything reasonable to happen, because that number 8 is relative to the 0 of the Fahrenheit scale. But when you deal with degrees Fahrenheit difference, then 8 is a meaningful multipliable by thing. And so one thing we've done in Wolfram language now is to introduce this idea of temperature differences. And they are different units. Degrees Fahrenheit and degrees Fahrenheit difference really are different units. And we've now sort of found a way to represent that with that little delta there. That represents a temperature difference. I like this notation. This is kind of something which I hope will become a standard notation for people and save lots of confusion. So for example, if I say, I've got two temperatures, one in degrees Fahrenheit, one in degrees centigrade. I take their difference. Now I get a temperature difference, in this case in degrees Fahrenheit. If I were to convert that to kelvins, then I would get an absolute temperature that I can then multiply by things and so on. Now, we've had the issue of what happens if you say 100 times 0 degrees centigrade. What does that mean? Does that give 0? Does it give something else? Well, we've now got that right, and now it gives a temperature in absolute temperature units. So that means, for example, that if we were to do a unit conversion here from degrees Celsius and degrees Celsius difference, of that same absolute temperature, we'll obviously get completely different results, because this is the temperature difference from absolute zero, and this is the difference from, am I getting this the right way around? That will be, oh yeah, that's from the zero of the Celsius scale. That's from absolute zero. Okay, so now we can do, this is unscrambled unit computations. They all just work. They all do the right thing. It's all good. Okay, so that's another out of our 10,000 units. We finally got to check off almost the last box of complicated things with units. There are a few more still to come, but this is the sort of most significant for at least physics purposes, is physical sciences purposes, our temperature units, which we now have really nailed down. All right, let's turn to a completely different topic. Let's talk about polynomials. We've had polynomials in Wolfram language since version 1, and you can always do computations of polynomials. Here's a typical piece of polynomial operation. We can do polynomial factoring, and we've been able to do this pretty efficiently ever since version 1. But if we do something like this, this is a much bigger polynomial. Let's see, how long is this polynomial? This has 999 terms. If I were to factor this in version 13.1, I believe it would take about 19 seconds. However, if I factor this in version 13.2, it takes only 0.3 seconds. So we managed to make factoring dramatically faster. It's a pretty rare time when you see something getting 60 times faster. But actually, even for even bigger polynomials, it will be even faster. The main thing that's happened here is that we're able to make use of some modern algorithms, and and also more significantly, we're able to make use of the features of modern sort of parallelizing hardware and so on, and make use of that for polynomials to be able to speed things up. Now, it's worth understanding, where do complicated polynomials show up? They show up a lot more often than you would expect. They show up inside lots of kinds of computations. I mean, if we were computing things with that nested square root, the minimal polynomial associated with that nested square root is this messy thing here, and then we're computing things with that polynomial. Okay, so these faster polynomial operations show up again in other places, like they show up in polynomial matrices. There's a polynomial matrix, and now we can go ahead and take the matrix power of that matrix, and this will be making use of the new faster polynomial operations. We can get, now we might say, let's get the determinant of that. Now in version 13.1, the result for that determinant is a big complicated mess, a bunch of nested polynomials. I think I have one. I think I have it. Do I have it here? Yes, I think I have it here. This is what 13.1 would give for this determinant. Okay, big complicated mess. Let's compute it in version 13.2. Ta-da, much simpler. Now we could get to that simpler result by saying, taking this whole mess here and saying expand that, we'll get the same result. But the whole point is, now the whole way we deal with polynomial matrices allows us to give the expanded result immediately without spending all that extra time computing all those intermediate pieces with the unexpanded result. Okay, if you make a bigger version of this, we get examples that are like 13,000 times faster and 60 million times smaller and so on, because with the whole nested structure, you kind of quickly get exponentially large expressions, which we don't now generate. Okay, here's another polynomial thing. Doing factoring of multivariate polynomials over finite fields. So factor this mod 2. Now, I have to say, I've been interested in this feature for like 30 years, because this comes up in studying additive cellular automata over finite fields, things like this. But I was kind of amused as we were adding this feature, looking back at our internal bugs database and so on. There's a comment in the bugs database from, January 1st, 1991, that was about, hey, what's happening with polynomial factoring of multivariate polynomials over finite fields, and somebody responds, I don't think the modular factoring is going to be implemented anytime soon. Well, in 1991, they were right, but soon has expired. 2022 is here, and almost gone even. And there we are with multivariate polynomial factoring over finite fields, now implemented in version 13.2. Okay, next topic. Let's talk about neural nets. We've got lots of neural nets that are implemented in our system. We've got a great framework for specifying new neural nets. But one of the questions is, when you have a neural net from the wild, you just kind of see it in some paper. Somebody says, oh, there's a neural net out there in the world. Can we get that neural net into Wolfram language? Now, what we're doing is to add capabilities to import neural nets as kind of black box neural nets that have already been trained, and it's just, here's a neural net, you can run it. So we're first working on the Onyx sort of standard for interchange of neural nets. There's a neural net from the wild, and we can, now the thing that's interesting is that how do you hook up this neural net? Well, it needs a certain encoder. You have to go read the paper that made the neural nets to figure out how is the encoder specified. What if this is a neural net that takes an image as input? How is that image specified? How big is the image? How are its parameters specified, and so on? So there's the result, and we can. This is making use of. This is now a network. This is an encoder network that is. It's an encoder that's specifying getting the image into the form that can be consumed by this external neural net. Okay, so if we do that, we can just run this external neural net immediately, just this thing that we got from the outside world. We didn't do anything. There's no this is literally just raw import. And then these are the encoders and decoders. Let's see if we can just run it. There we go. So it managed to cartoonize, as a cartoonizing network, it managed to cartoonize that Mount Rushmore. So it's pretty cool that one can just take sort of a neural net from the wild and just run it immediately in Wolfram language. And this is that capability. Okay, next topic, trees. So we've had let's see if we can get I don't think I'll let the seed. Why bother with the seed? Let's live more dangerously. Okay, here's a random tree. And so one of the issues is that random tree has quite a lot of has sort of things that overlap in this rendering. So we can say, if we want to get around that, we can say max displayed children for all nodes is just 3. And so what we'll see here is then some of these nodes, their descendants will be omitted. And so it says 4 total. So there's 1 missing here because the 3 you see and 1 you don't see. So there's a way of taking even a very large tree that might be some, XML tree, or it might be some mathematically generated tree, and being able to generate, to make it so that you can visualize it more easily. There's a global $max displayed children that is typically set to 10, which specifies how you will prune out the parts of the tree that you don't want to see. I noticed a comment on the live stream from Seth about Onyx files, asking for more examples about encoding and decoding. Yeah, I mean, that's one of the many kind of underbellies of the neural net world is, in the end, whatever you have, whether you're getting in a sound, a picture, whatever it is, it's got to turn into an array of numbers. And how does that work? And, if and what are the ways you do that? And it's sort of a place where you have to really interface with the literature of the paper that defined this neural net. It says this neural net expects blah blah blah. There isn't really a standard for this. We've tried to contribute things to things like MXNet to contribute some kinds of encoding capabilities to these standard systems, but I have to say, I think that we are now on our already on our fourth kind of intrinsic back end for our neural net system, and we expect that we'll be on our fifth one before too long. So it's a bit of a moving target. And this sort of interface between what we provide, which is very rich in terms of how you specify encoding and so on, how that matches with what people say they need in terms of encoding, tricky issue. All right, let's go on. Let's talk about calculus. I showed some examples earlier about polynomials where we're now seeing much simpler versions of solutions. Same things happen for differential equations. This equation gave a hugely complicated mess in version 13.1. Now it is still complicated, but it's a much more civilized mess. It doesn't go on for pages and pages. That's a thing that we've got a bunch of new algorithms for differential equations with constant coefficients, or so-called LTI systems in engineering, linear time invariant systems, well, a bunch of new algorithms that make for better, faster, smaller, easier to read solutions for those kinds of things. I mean, it's one of the things you might think is, oh, you're computing the answer to a problem. I'm just going to compute the answer. It's going to be a number. Well, actually, it's not just a number. You have to know the precision of the number and all this kind of thing. When you're computing an algebraic answer, it's not just, well, there's a whole giant family of equivalent algebraic expressions, and some may be more to your liking than others. And that's sort of, it's almost an aesthetic judgment, but now we're much better at generating nice compact results from differential equations. Okay, another thing is we introduced in version 13.1, we introduced fractional derivatives. So we can compute the half derivative of sine x. This is something, so this is now the numerical, the new in 13.2 is numerical fractional derivatives. And there's the result for the numerical fractional derivative of sine x, showing that it goes imaginary on the negative axis there. Likewise, there's some, we can do asymptotic solution of fractional differential equations. This is the Caputo D fractional derivative is what one needs to use for these kinds of equations. And there's the result for getting a series solution for that fractional differential equation. Okay, another topic, cluster analysis. One of the issues here is given that we do cluster analysis, we might want to analyze what we get in the clusters in cluster analysis. And one of the things we've now added, so you'll see there are different numbers of clusters here, and sort of the you can decide, whether you like that's just one cluster, two clusters, and so on, which one is the best set of clusters to use. And so now we've got this notion of clustering measurements, which allows you to get kind of diagnostics about clustering that gives you a way to estimate, for example, what's the best clustering, the right number of clusters to use. Okay, next topic. You can tell that we are able to import a lot of kinds of things because the thing we added to import now in version 13.2, one of the new import formats is import format for chess. And so there's a chess board representation, and there's the corresponding chessboard. We can import, for example, a collection of we can import a collection of games. Let's import. Here we go. Let's see. Got this. This will give a collection of chess configurations, and I think we can take. All right. Let's go ahead and import that. That will give a bunch of chess configurations. And let me just to make things go a little quicker, let me just take the first 10 of these, and we can now just put some tech together and make a video from the configurations of the chessboard that we imported this way. We can play the video, and there we go. A game is being played before us, so to speak. Now, we do have other formats that we've added in version 13.2. We've added import of OpenStreetMap format. That's a pretty nice thing for letting one. In fact, I should have given a better example of this. For letting one import road networks and things like that. We'll be having some more capabilities for analyzing road networks in a subsequent version. Also, the GXF format, another geo format, has been added there. Okay, next topic. Runaway computations and their control. Okay, when I first developed forerunner of mathematical and Wolfram language, SMP, back in 1979 to 1981, one of the things that I wanted to do was to have it be based on transformation rules for patterns. Same idea as Wolfram language. It turned out to be a pretty good idea. I didn't know it at the time, but it turned out to be a very strong idea that I kind of, in a sense, was derived from sort of a condensation of things people had done in mathematical logic years earlier, and just the sort of quotes obvious thing to do when you're doing kind of symbolic operations. But my idea was, you've got transformations that can be done on symbolic expressions. Just keep doing transformations until you can't do them anymore, and keep going until you reach a fixed point. And I knew a bunch of theoretical computer scientists at the time, and they looked at me and they're like, your system can't work. It's just going to blow up all the time. It's theoretically impossible. Why did they say that? Well, they said that because if you type x equals x plus 1, it's going to, if you have the operation of your system be such that it just keeps evaluating things until they no longer change, and it's a symbolic system, x equals x plus 1 simply never terminates. And this has been an issue. It's very interesting. If you're interested in the kind of the language design kinds of things, there are always kind of nasty sort of, I don't know, landmines or something that you could sort of step on in different kinds of designs you might make. And the question is, you're going to have these holes somewhere. The question is, will those holes be important in everyday usage of the system or not? The only system that has no holes at all is a system that does nothing. There's sort of generalizations of that principle when you think about physics and kind of axiomatization of particle physics and God knows what else. But for the purposes of language design, the only language that does nothing weird is the language that does nothing. So you always have weirdness somewhere. The question is, do you typically step on those things, and do they cause you trouble? Turns out, my friends, the computer scientists, weren't right that this would just sort of blow the system up, even though theoretically it does. In practice, one doesn't run into x equals x plus 1 very often, but occasionally one does. And there are a collection of absolutely bizarre kind of issues that come up from this sort of the system protects itself by hitting this recursion limit. It kind of has to protect itself because it's doing these evaluations on the stack, and operating systems tend to allocate processes. Even today, 36 years after we start, well, 43 years after I started the design of these kinds of things, it's still the case that if you run out of stack space, your process will crash. And it's not, and you tend to allocate a fixed stack for the process. So you kind of have to protect yourself somehow at the application layer. And we do that with $recursion limit. And one of the issues is, let's say you reach $recursion limit, but the thing that you are using to represent that recursive output itself has recursion in it. Then you can go on and you can recurse on the recursion, and you can tie yourself up in knots and eventually crash. So in version 13.2, it's kind of the beginning of a much more principled way of controlling infinite evaluation. By the way, coming in the future, as part of our kind of multi-computation direction, we will be actually supporting infinite computations and the ability to kind of look at slices of infinite computations deeply related to the operation of time in the universe, which is essentially an infinite computation that's running, and our experience is various kinds of slices of that computation. And we want to be able to do the same kind of thing in our language. But most of the time, most computations people want to do in the way that they think about them right now are you give input, crunch, 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 you get fixed point output. This is a case where you don't get that. This is the beginning of dealing in a much more principled way with infinite computations. We have this notion of a terminated evaluation that shows us why it terminated. In the future, we're going to have some other things which give you information about that terminated evaluation. Let's see. So yeah, there's all kinds of funky stuff that happens. So one thing is this now, as you make the evaluation graph, this is now going to generate two terminated evaluations, and they are separate branches of the evaluation graph. In the past, you would hit a single recursion limit here, but this is now has the two separate branches of recursion. Okay, there are some other things that are a little bit subtle to do with propagate aborts that have to do with the question of when you hit a time constraint or a memory constraint or an explicit abort, exactly how far that unrolls things in the system. All right, moving on. Another thing, it's kind of a sort of simple utility function we always like to add. I like to kind of analyze my own usage of Wolfram language and kind of get a sense of other people's, of what are some things where you just keep on needing to do that. Here's one, position largest. What is the position of the largest element in this? Now, obviously, this is not hard to compute. It's just the position of the max element, but this is just one function that gives you the maximum element, and it deals in a nice way with ties and so on. So just a simple utility function. Okay, another piece of another straightforward thing. This is a very simple kind of user interface thing. What is that object? Is that a graphic? Is that a graph? Click it. It's got a purple border. That means it's a graph. If I do the same kind of thing with, if I make a graphic, you'll see that it has an orange border. And you know, you might, it's often very hard to remember colors, but it is the case. One of the nice things is that by the way, these have actually both existed in the past. Now we've added same kind of thing. Let's see if I can get this. Well, let's just say picture of an eel. Okay, there's an eel. Now, if I click the eel, you'll see that it now has a blue border, and that's the way that we're indicating. It could be a thicker border here, I have to say. That's the way that we're indicating that this is an image as opposed to a graphic. And there are a variety of other colors, like trees have a green border and so on. Simple user interface thing, helps one out occasionally. Oh, I thought that was a graph. No, it's actually a graphics, etc. Okay, along the same lines of hinting, here's another one. This is when you're typing and you put your cursor right here, we now light up much more brightly the brackets that are the enclosing brackets. And we have specific rules for, so you can kind of see which function are you in. You click there, what's the head, what's the function that you're in with that thing. So if I pick a slightly more complicated input and I'm clicking here, okay, I can immediately see this contours thing. That's part of the contour plot. Useful. Now we have one other color that we use, which is an orange color, and that orange color is representing the delimiter that you're in. The yellow represents the function that you're in. The orange represents the delimiter you're in. So if I go here, I'll see the orange going around the brace brackets. Here I can see the here I'll only see the function thing, but if I go here, I'll see the orange for my closest delimiter and then the yellow for the function that I'm in. Okay. So I find this really convenient, actually. Just making these brighter and making the rules simpler for when things light up. It's just a very convenient way to figure out navigating around the system. All right, another little convenience. We've got, you know what I need to do? I need to remember that I should clear X, otherwise it will blow up at some point in the future. Okay, so I got A, B, C. That does do 3 different operations. It's all in one cell. We can now do the thing of divide cell, Command-Shift-D on a Mac, that now divides that cell at the position of the appropriate. So if I say A plus 1 plus 7 plus 6 semicolon, and then I go C plus 8 here, and I say divide cell, that will divide in those two, at the position, those two expressions in different cells. Just a convenient thing. Another just a convenient thing. Oh my gosh, I have switched off. Wow, I shouldn't have done that. I switched off our beautiful default toolbar here. How could I have done that? There is our beautiful default toolbar. Doesn't get magnified, but if you can see it, our beautiful default toolbar, if I go to the thing that is change the features of the cell, there's a piece here that says frame style. And so now I can go and I can, for each of these pieces of the frame, I can go and let's see, how does this work? What is this doing? I am confused. Maybe I didn't have anything selected. I select that, pick the frame style, and then, oh yeah, when that's really odd. I'm not seeing the selection. That doesn't look right. Well, something is there's a nice interface here for giving frames around cells, but for some reason it is not working for me. Let's see, I can make it bigger. Oh, there we go. There's that frame. Right. It was kind of weird. Something went wrong here. Okay, there we go. So there's the top frame of the cell, et cetera, et cetera, et cetera. Just a nice interface for putting frames around cells. Seth is commenting about strings in output, and we've been talking about that. And actually, the idea that an output string would have a different color when you mouse into it is a good idea, and we should look at that. Thank you. Okay. Another big area, and kind of the last big area I get to talk about here, is about the compiler. And this is a complicated area. And if I'm lucky, nope. Okay. Our experts are not on call for this. All right, so I'm going to have to tell you about the compiler myself. The compiler is a tremendously important part of kind of underlying technology for Wolfram language, and it's part of the sort of major future of our technology stack. And it's rather spectacular. It's also very complicated. And in a sense, what is the point of the compiler? The point of the compiler is that we're trying to say, we know what your code is supposed to do. Now let's cast that code into something which is more efficiently implementable at sort of a low level of your computer. And typically what needs to happen is, the most important thing is your computer has instructions that deal with integers and real numbers and certain layouts in memory and so on. All of that stuff you don't have to worry about when you're using Wolfram language. We have to worry about that. But we're worrying about that in a sense generically. We want to be able to specialize the worrying for particular inputs and for particular programs. And in some cases, we can't know what you want. You've written a function, and that function, I don't know, computes zeros of the zeta function minus a half divided by I or whatever else. And you might reasonably want to assume the Riemann hypothesis and be sure that those numbers that are coming out are going to be real. And you might be very happy just assuming you can store those numbers at a machine code level in a register as real numbers. But we can't know that you want that. The code that you've written does not tell us that intent. We can guess that, this might usually be an integer, but that's not necessarily good enough. Sometimes we'll go ahead and the compiler will guess that, and if it turns out it's not an integer, it will generate an exception, et cetera, et cetera, et cetera. But how can you give hints and so on, and how does that all work? So in the compiler, there is a notion of like a type specifier. That's a type specifier for a function that takes two 64-bit integers and returns a 64-bit integer. And this is what you do to compile something which is a function that takes an 8-bit integer and returns that integer plus 100. And by the way, one of the big projects is to compile the compiler, which is going fairly well. And once that's done, it will be ridiculously, dramatically faster to do compilation. Now, here, we're not telling it what the output from this is supposed to be. So we're just saying, you feed in an integer 8, and you're just going to add 100 to it. Now, of course, if I fed in some integer 8s, like, for example, I fed in, let's say 200 here. It's a perfectly good integer 8, but so maybe that isn't an integer 8. Hold on a second. Do I need to go? Okay, that's fine. But then if I get to something that is above, what do I want to get to? Above, let's see, if I want to get above, let's say I say 110 here. Oh, no, that's still working. Where's going to be the breakpoint? It's going to be 150 or something. Boom. Okay, that didn't work. So yeah, an integer 8 goes from minus 127 to 128. So this is what I'm looking for, is something that has, there we go. No, what's going on here? The basic point is, I see, I know what's happened. I know what happened here. This thing isn't using compiled code. This thing is defaulting to non-compiled code whenever the x plus 100 no longer fits in an integer 8. Or actually, we're not telling it should go in an integer 8. Here we're going to give it a hint. This is a new thing, type hint. Type hint says, I really want this to be an integer 8 that's coming out. And so now if I do that 127, I will get compiler code, runtime error code, reverting down compiled code, integer overflow. Because we told it, I really want that thing that comes out to be interpreted as an integer 8. So this idea of a type hint is a way of you giving it more information about what you want, how you want it to interpret things so that it has a better chance to do compilation. Okay. The next thing about, and by the way, yeah, type hints are a thing you can leave lying around your code. You can put a type hint in anywhere, and if I just say, type hint this, that type hint will just evaporate in ordinary evaluated code. But if the compiler sees it, it will take the hint and do what it should do. There's another new thing, which is if compiled, which literally, we say if compiled 6, otherwise 7, and it'll say 7 here because it hasn't been run through the compiler. But if that was in compiled code, it would give 6. And so that's a useful thing to be able to have in your code any way you want. You can say, well, if it's going to be compiled, do it this way. If it isn't going to be compiled, then it's better to do it that way. And you can just put that in your code and have one piece of code that can deal with both being compiled and not. Okay, another aspect of the compiler is you defined a function here. And now you want to make use of that function in a compiled function. Well, there's a new concept of a down values function, which allows you to pull in to the compilation process the definition of that function that has been defined with down values. And so this is now pulling in that definition to create a function that will be from machine integers to machine integers. So this is important when you have a big block of code, like in our efforts to compile the compiler. This is a critical piece of that technology stack, is the ability to kind of daisy chain this compilation process through down values function. So kind of analogous to the kernel function, where you can have a callback from compiled code into evaluated code using kernel function. Okay, another area. This is also about compiled code. This is about dealing with large libraries and integrating them with Wolfram language. This is pretty neat. So here's a packlet. It deals with a thing called GEOS, which is a big library for geometric computation. And this is a packlet that's been built for GEOS. And we can now say we load in all those functions. And now we are going to see how we can do this. ToGeos is a function defined in GeosLink. Random polygon is a polygon defined in Wolfram language. When we say ToGeos, what we're going to get back is this thing here. This is an alien creature that has been kind of tethered to our Wolfram language system. So what really happened? GeosLink is a dynamic library, big dynamic library. It was loaded into the process that we're running, the Wolfram language session we're running. Then this ToGeos function created data inside that that was sort of owned by that library. And so it created a managed GEOS geometry managed object. So this GEOS geometry thing is a data structure that was in the C code of GEOS. And now this is something that is being managed by Wolfram language, but is a structure that Wolfram language now understands because the compiler, using compiler technology, we've got this kind of mapping from the raw C struct into Wolfram language code. Okay, so now we can take this object, which is some weird alien creature, this type product thing, and we could just say, run a function on it. Okay, we get another one. Okay, now we can say, from GEOS of that, and we can say, make a graphic from GEOS of that. And so what's happening here is that we've got this external library, big complicated external library with all its C interfaces, and we're able to now kind of instantaneously produce we're able to very easily make a link to that library. And then we're able to use that library as just another thing that we can call from Wolfram language. It's not as beautifully designed in terms of the interface as the things we go to so much trouble designing for Wolfram language, for sort of the core Wolfram language. But the good news is you can access these things and you can put your own design, your own Wolfram language design on top of it and make it as nice as you want. Okay, so let's see if I can actually do this. This may be disastrous, but I can try it. Let me try and open the, here we go. Let me try and open, this could be truly dangerous, but I'm going to actually open the, this code. So let's see, library resources is showing me the versions of that library. I wonder if I can make this bigger somehow. Let's see, is there a view option? Oh, no, there isn't a size. Sorry, guys. Oh, there is a size, sort of, except it only goes up one size. Okay, well, I'm sorry. Here, worst case is, let me just show you this. When in doubt, use your own technology. There we go. There's what that directory looks like. There are two versions of this library that I have. The Packlet Manager figured out this was a Packlet that was built, that this is a Packlet. The Packlet Manager, when I knew that I had a machine of this type, so it only downloaded those versions of the library. Now, okay, what does it actually look like? Let's see, where is this? This is in, where do I want to go? Library resources, and let's say here, and where do I go here? Now I want to go back up. Maybe it's in geoslink.wl, but it thought it was in a different file. Is it in core? Oh yeah, here we go. Okay, so here I'm going to show you the actual code that is the glue code that actually connects us to this big library. Okay, and it's now having to specify, it's specifying library function declaration of, I mean, this library has a lot of stuff in it. So it's specifying kind of what GEOS geometry GEOS contains is this library function declaration, and it is probably a function that takes two GEOS geometry objects, returns a C char. Here we've got probably the declaration of GEOS area that contains a raw pointer with C doubles in it, et cetera, et cetera, et cetera. I just want to emphasize that the thing you're getting by using Wolfram language is that you don't have to know about all of this stuff. This is how you connect Wolfram language to kind of the sort of the world of giant C libraries and other kinds of things. But I just, to give you a sense here, this is how this is sort of what things look like in a function declaration GEOS distance within. This is a managed GEOS geometry type and a C double mapping to a Boolean, and this is now what that function actually, what the function GEOS distance within, how that's defined. But what's important here is that this function declaration tells you kind of how to map all these things into the actual raw C types of the library. And somewhere here we probably have meshes and hulls, okay, Voronoi meshes. We probably have just a pure, GEOS intersection. Okay, that's create a type instance of a managed type, which is a library function of GEOS intersection of these things. So, I mean, this is just to understand. I mean, the simplicity of this relative to what one had to do before is absolutely transformational. I mean, this is, the time it takes to connect a complex library into Wolfram language has just been divided by some huge factor. So this is what it kind of looks like, deep down underneath, so to speak. And in the end, what this is doing is creating a new construct called a compiled component. And what one's doing is using the function declare compiled component to specify these different pieces of the linkage that will happen, and that's how you build up this this link. I mean, I have to say, I think that this is something that is really, in terms of, you know, whatever exists out there in any language, but this is, you know, and most languages, sort of the ultimate interface is kind of a C-like interface, just because that's how raw, it's a good wrapper around kind of the raw representation of things in a machine. This is a way to sort of smoothly interface to any such thing in Wolfram language and get the advantage of all of the kind of existing structure and interfaces and knowledge and so on at Wolfram language, and connect it to whatever raw libraries exist outside. Now, remember, we've also got, for interpreted languages, we've got this whole mechanism where you can go ahead and pick your favorite interpreted language. I don't know, you can pick something like the shell, and you could say, for example, you know, let's evaluate a shell command, and this is now running. There's the shell command. I could evaluate a Python command or any one of these languages here, Java, whatever else, or an SQL command for that matter. These are interpreted languages. This is the sort of ultimate robust way of communicating with compiled languages and building things that can now integrate with the compiler. So for example, once I've got this GEOS library in there and I've got its data types defined, I can now use those data types in code that I write in Wolfram language, which is then compiled, and it will then be as if one was basically writing low-level C code. And, you know, for us from 36 years ago, you know, the original core kernel of Wolfram language was written in an extension of C. I don't expect we'll have to write much C code ever more. We will be using our own compiler technology, even for the things for which we in the past would have written sort of very low level, you know, C, C++ code and so on. That is simply unnecessary at this point. And there are just tremendous advantages from that, because we have a much higher level, more analyzable, more meta-programmable access to a lot of technology, access to a lot of essentially theorem proving about what the code does, all those kinds of things, by being able to write, and also immediate integration into everything else that Wolfram language does. So I think this is a sort of, from a software engineering point of view, this is an exciting development. Let's see, just to summarize, and then we're wrapping up here. We've just got all kinds of you know, new things that are that have happened in this version. I've expected that would just do something here. Wow, that was not what I was expecting. That was not the thing I was expecting to cause me trouble, although I know it does. Oh, yes. My mistake. Oh wow, I just loaded into my GPU some horrendous thing here. This is just an effect that is a blurring effect. We had the drop shadowing effect that we added previously, and this is now just another effect that's very GPU based kind of rendering effect. There are other things that have come, some new things in parallelize, some new capabilities in synthetic geometry, new capabilities in image stitching, a bunch of specifics in those kinds of places. But anyway, that was my basic walkthrough of version 13.2. I should say here's a word cloud of some of the new things that have come. And what is that? That's not a thing. Why is there something in our word cloud that is a fun? Oh no, this is not us. This is not the core language. I'm sorry. This is a word cloud of things in the function repository. And one of the things that's the function repository is really going great. And thank you to people who might be on this live stream who've contributed to the function repository. The function repository is just it's a terrifically useful resource. It's really something that's been made possible by the whole design structure of Wolfram language, because you can add just one little function here, and look at this, we'll actually go there. And this function spin show, for example, we just type it in here, we copy it in, we run it, and it'll load that resource. We don't have to know anything, we don't have to understand where there are libraries or anything else, and it'll be singing and dancing and spinning right there. We could say whatever it is. I mean, any of these kinds of things. We're just immediately able to do computations where we've made use of a lot of structure that already exists in Wolfram language, and what we're doing in the function repository entry is just adding that one little piece of icing on the cake, so to speak, that lets one do something. So this is, what is this? This is conforming colors. Okay, so this is making colors probably be all. I should stop this because it is wiggling my notebook up and down as it spins. Right, so this just made them all CMYK colors and so on. But the important point here is this is a way of kind of adding pieces to the system. I thought we had a word cloud actually also of what's new in 13.2, but and I think I might have, there's a full list of what's new in 13.2 that you can find in the documentation. But let's just show you that and then wrap it up for now. It's probably at the bottom. Don't forget, by the way, people, that there's this custom guide page capability now that lets you make a guide page of your own favorite functions that you can conveniently store here and also in the cloud, so that you can always get to them from this root guide page. If I go down here, this is the summary of all new features in 13.2, showing a bunch of things I've talked about here today and a bunch of things that I haven't talked about today. But this is kind of everything that's new. All right, well, I think that's what I had to say. Thank you for joining us, and please download your 13.2 or use your 13.2 in the cloud. It's what will come up if I go to the cloud here and create. Let's go to the cloud and create a new notebook and say, what version are you running? And it's 13.2. There you go. That's it's not for today because it was being tested for a month or so before it was put on the cloud. Check it out, use it in the cloud, use it on the desktop, download it. Exists on all our platforms, and have fun with it. Let us know your feedback. Tell your friends. Get more people to understand our technology stack. I've taken to saying that a lot of the technology we provide is kind of artifacts from the future, and sometimes I feel that some of the things we provide are kind of artifacts from 50 years in the future. Some of them maybe from less time in the future, but I think I also have now noticed that those who understand our technology stack and our language have gained a superpower. That it's one of those superpowers that you didn't have to be born with, so to speak. You can just learn it, and once you have that superpower, you can do all these amazing things with Wolfram language that seem to other people like they're pure artifacts from the future. Anyway, well, thanks for joining me here today, and have fun with this new version. And we're looking forward to, we've got a big pipeline of things that we're working on, and we look forward to continuing to deliver great new versions of Wolfram language going into the future. So thanks a lot, and bye for now.